Have you ever really stopped to think about what makes a modern factory work? I mean, it's not just a bunch of gears and robots moving around. There's this hidden, super intelligent network, kind of like an invisible nervous system that's coordinating every single move with just mind-blowing speed and precision. Today, we're going to pull back the curtain and map out that entire system, layer by layer.
So what is this invisible nervous system we're talking about? Well, it's this amazing hierarchy of digital senses, muscles, and brains that has completely changed the game for how we make, well, everything. So let's dive in and break it all down, starting from the ground up. All right, every control system, no matter how complex, starts at the most basic level you can imagine. You need parts that can perceive the world, and you need parts that can act on it. In the factory, we call these the senses and the muscles. First up, let's talk about the senses. A sensor's job is actually pretty straightforward. It just measures some kind of physical condition, like temperature or pressure, maybe even vibration, and then it translates that into an electrical signal that a computer can actually understand. And you guessed it, if sensors are the senses, then actuators are the muscles. These are the guys that get things done. They take an electrical command and turn it into real physical motion, popping open a valve, spinning a motor, or moving a giant robotic arm. Now, this whole partnership is perfectly shown by the safety valve on a simple gas furnace. You have a sensor, a thermocouple, that feels the heat from the pilot light and creates a tiny electrical current. That signal tells the actuator, in this case the gas valve, hey, stay open. But if that flame goes out, the signal disappears, and that actuator instantly slams the valve shut. It's a beautifully simple control loop that prevents a total disaster. Okay, so we've got senses, and we've got muscles. But what's in the middle? What connects them and makes the actual decisions? For that, you need a brain. A local brain that can think and react in real time. Before we had modern computers, this kind of control was handled by these massive, clunky panels of physical relays. I mean, they were hardwired, they were slow, and honestly, they were a total nightmare to troubleshoot. The modern answer to all that is the PLC. It's programmable, it's incredibly fast, it's compact, and it's way, way simpler to figure out what's wrong. And this is it, the Programmable Logic Controller, or PLC for short. The best way to think about it is as a super rugged industrial-grade computer. It's designed for one job, to be the dedicated brain for a single machine or process. This thing is built like a tank to survive the heat, the dust, and all the electrical noise of a factory floor and just keep on working, day in and day out. So, how does this little brain think? Well, the PLC runs on this continuous, high-speed loop. It's called the scan cycle, and it happens in just milliseconds. First, it reads all the inputs from the sensors. Then it runs through its programmed logic, and finally, it updates all the outputs to the actuators. It just repeats this cycle, read, think, act, over and over, thousands of times a minute. Now, inside that think step, the PLC often uses this really powerful math trick called a PID controller. This is what gives it such incredible precision. Instead of just turning something on or off, it's constantly calculating the tiny difference, or error, between where it wants to be, like a specific temperature, and where it actually is. Then it makes these tiny, constant corrections to stay perfectly on target. Now, PLCs do have a more powerful cousin, the PAC, or Programmable Automation Controller. Think of it this way. A PLC is the perfect workhorse for controlling one machine really, really well. A PAC, on the other hand, is designed for the big, complex stuff. It's got more firepower, more advanced programming, making it the right choice when you have to manage entire interconnected systems all at once. So a single PLC is great for one machine, but a modern factory has hundreds of them. So how do you manage all of that? Well, you have to zoom out. You need to go up to the supervisory level, to the central command center of the whole operation. This is what we call the control hierarchy. Right down at the bottom, at level 0, you've got your field devices, our trusty sensors and actuators. They report up to level 1, which is where the PLCs live, making all those local, real-time decisions. And then those PLCs report up to level 2, the supervisory computers, which give human operators a complete overview of the entire factory floor. At this supervisory level, you're going to hear a few key acronyms. An HMI, or human-machine interface, is basically just the screen you use to control one machine. But a SCADA system, that's the real command center. It collects data from all the PLCs, giving operators that bird's-eye view of the entire plant. A DCS, by the way, is a bit more specialized, usually built to manage huge continuous processes, like you'd find in an oil refinery.
Okay, but for this whole pyramid of control to work, every single device, from the simplest sensor all the way up to the main SCADA system, has to speak the same language. In the world of automation, we call these languages communication protocols. Now, two of the biggest languages you'll find running on industrial Ethernet are Modbus TCP and Ethernet/IP. And they really have two totally different philosophies. Modbus is all about simplicity and being able to talk to absolutely everything. Ethernet/IP, on the other hand, is a much more sophisticated, feature-rich language. Just think of Modbus TCP as the universal translator of the factory world. It's simple, it's open source, and it's supported by pretty much every device on the planet. If you've got a situation where you have to connect equipment from 10 different companies, Modbus is the reliable, common language that just makes sure they can all talk to each other. No fuss. Ethernet/IP is the high-performance specialist. It's really deeply integrated into the Rockwell Automation and Allen Bradley world, and it offers some seriously advanced features like deep diagnostics, automatic device discovery, and even high-speed motion control. If you're building a system on that platform, the level of performance and convenience it offers is it's really hard to beat.
So let's put all the pieces together. Let's see the complete picture of our factory's amazing invisible nervous system.
Everything, and I mean everything, starts on the factory floor with the senses and the muscles. You have hundreds, sometimes thousands, of sensors constantly gathering data from the real world, while all the actuators are standing by, just ready to act.
All that raw data then flows up to the local brains, the PLCs. Each one is making instantaneous decisions for its specific task, running through its logic thousands of times a minute to keep everything in perfect control. And finally, the data from all those individual PLCs gets bundled up and sent to the SCADA system. This is central command. This is what gives human operators the high-level view they need to manage the entire factory. It's just a really elegant and incredibly efficient hierarchy of control. So from a simple sensor up to a PLC and all the way to SCADA, that is the brain of the modern factory. It's a system that gives us an incredible level of consistency, efficiency, and safety. But it leaves us with one last big question. If this is the factory's brain today, what will the factory's mind look like tomorrow?